This video is about using LHpitals Rule to evaluate limits that happen to be indeterminate forms. So here are 7 types of indeterminate forms. I've actually seen several of these before earlier in this course. We've got a 0 over 0 indeterminate form. Here's an example of that. Let's say we're taking the limit as x approaches 2 of x squared minus 4 over x minus 2. If I just substitute x equals 2 into this, I get 2 squared minus 4, which is 0, over 2 minus 2, which is 0. So that makes that a 0 over 0 indeterminate form. I put it in quotes because we can't really divide by 0. But we call this an indeterminate form because we're really not sure what the value of this limit is going to be if we get 0 over 0 when we substitute x equals 2. It's indeterminate. If I've got a function in the numerator that's approaching 0 and a function in the denominator that's approaching 0, if the function in the numerator approaches 0 faster than the function in the denominator, well then we'll have 0 over a non-zero number in the limit, and 0 over a non-zero number will be 0. So our limit will be 0 if this one gets to 0 before this one gets to 0. Now, if this function in the denominator approaches 0 faster than the function in the numerator, well then I'll have a non-zero number divided by 0. So I've got a non-zero number divided by a number that's very, very close to 0. So remember what we had for limits like that. If you have a non-zero number over 0, you get plus or minus infinity. So if this function in the denominator approaches 0 faster than this function, we could get plus or minus infinity. So if this one goes to 0 faster, we get 0. If this one goes to 0 faster, we get plus or minus infinity. If they happen to go to 0 at the same rate, we might get a number. We might get just some number in between. It might be 17 or something like that. So it's indeterminate. Now, earlier this semester, we learned how to evaluate limits with this type of indeterminate form. We had 3 different techniques. One of them was factoring and reducing. This one can be solved that way. We said, if we're taking the limit of this function, that's the same as taking the limit of this function. And that is the same as taking the limit of this function. Now this function is not identical to this function, but they have the same limit because as x approaches 2, we're taking the limit as x approaches 2. X isn't equal to 2. So this x minus 2 is not 0 at that point. I end up with a number divided by itself, and a number divided by itself is 1. So the limit of this function is equal to the limit of this function. And this function is continuous at 2. So I can just plug in 2, and the limit happens to be 4. So that's a 0 over 0 indeterminate form that we were able to evaluate using factoring and reducing. And there are also infinity over infinity indeterminate forms. You've seen some of those. We saw some of those earlier this semester as well. Maybe you see something that looks like this. The limit as x goes to infinity of 2x cubed minus 4x plus 3 all over 1 plus 2x squared minus x to the 4th. Well, the numerator, as x approaches infinity, that numerator approaches infinity. We sort of look at the dominant term and we say, if x is a really large number and I cube it and I multiply by 2, I'm going to get a really large number. So the behavior of that dominant term determines the behavior of the whole numerator. And x approaches infinity because that term approaches infinity. Or excuse me, that the numerator approaches infinity because that term approaches infinity. The same thing in the denominator. I look at the dominant term. As x goes to infinity, the negative x to the 4th goes to negative infinity. So this is an infinity over negative infinity indeterminate form. But we had a method for dealing with that. If we've got a polynomial over a polynomial, we can divide by the highest power of x in that denominator. It's really just dividing by the dominant term, like that's the idea. And if we do that, that will get rid of that infinity over infinity indeterminate form. So when we divide everything by x to the fourth, we get 2 over x minus 4 over x cubed plus 3 over x to the fourth. In the denominator, we've got 1 over x to the fourth plus 2 over x squared minus 1. Now, because we divided by x to the fourth, we get a constant in the denominator plus a bunch of terms that are approaching 0. This approaches 0, that approaches 0, that approaches 0, that approaches 0, and that approaches 0. So we end up with 0 over -1. So we get 0. So this is indeterminate as well. We happen to get 0 for this function, but we could have just as easily gotten positive or negative infinity for this function as x goes to infinity. Or we could have gotten like 17 or 4 or something like that. It all depends on the relative rates of growth, though. It depends on which of these functions approaches infinity faster. We're saying, as they go to infinity and negative infinity, are they going at the same rate? If they're going at the same rate, I would expect a 4, or not a 4, but a constant, just some finite limit in between negative infinity and infinity. But if they're approaching infinity at different rates, I'll either get 0 or I'll get plus or minus infinity. So let's think about it. If this is approaching infinity and this is approaching negative infinity, and this one is approaching infinity faster than this one, I will eventually have infinity over a finite number. A very large number over a finite number is going to be a very large number, so we'd get infinity. Now, if this one was approaching negative infinity faster than this one was approaching a positive infinity, we'd have a number divided by something that's very large and negative. So a finite number divided by a very large negative number, it's going to negative infinity. That I would expect to be 0. And now if they're approaching infinity and negative infinity at the same rate, we might get a constant. In this case, this one was approaching negative infinity faster than this one was approaching infinity, and so we got 0. Here, the numerator and denominator were approaching 0 at the same rate, and so we got 4. Here's another example. I've got this expression now. As x goes to infinity, the numerator goes to infinity, so does the denominator. That's infinity over infinity. We can eliminate this indeterminate form by dividing by that dominant term in the denominator. The dominant term is a 3 to the x. It's going to be very large compared to that 5. That 5 is not going to do much as x goes to infinity. It's not going to affect the limit very much at all. So 3 to the x is reduced, and we just get an x in the numerator. And then in the denominator, we'll have a 5 over 3 to the x plus 1. As x goes to infinity, 3 to the x goes to the infinity, or goes to infinity. So 5 over something really large is something really small. That goes to 0. And I end up with something that's growing very fast, growing very large, excuse me. X is going to infinity, and we're dividing it by 1. So something that's approaching 1. So the limit ends up being infinity. So this is a case with an infinity over infinity indeterminate form, where the numerator went to infinity faster than the denominator. So this grows faster than this does, and since this gets to infinity before this does, we get infinity. So if this gets to infinity before this does, we get infinity. If this goes to negative infinity before this does, we get 0. If they approach infinity at the same rate, we might get a constant. We just don't know. But these are the techniques that we used before. Now, LHpitals Rule is for problems where none of these older techniques apply. Now, sometimes the older techniques do apply, and you might prefer to use LHpitals Rule anyway. So here's an example where the old techniques do not apply. Let's say you want to find the limit as x approaches 0 of e to the 3x minus 1 over sine of x. Actually, let's approach from the right. Well, as x approaches 0, sine of x approaches 0, because sine of 0 is 0. And if x is 0, we get e to the 0, which is 1. 1 minus 1 is 0. So this is a 0 over 0 indeterminate form. But here, I can't factor and reduce. There's nothing to factor. I can't divide by that dominant term in the denominator because I'd be dividing everything by sine of x, and that would lead to exactly the same thing and have a 1 in the denominator and this over sine of x in the numerator. So it wouldn't change anything at all. So we need a different method for evaluating limits like this. And that method is called LHpitals Rule. So LHpitals Rule says the following. If you have an infinity over infinity indeterminate form, so if we take the limit as x approaches c, of f of x over g of x, and that is a 0 over 0 indeterminate form, or an infinity over infinity indeterminate form, and we really don't care about the sign, it's plus or minus infinity over plus or minus infinity as an indeterminate form, then the following is true. Remember what we were just talking about. It's all about rates of growth. We're saying if this approaches 0 faster than this approaches 0, we get 0. If this approaches 0 faster than this approaches 0, we get plus or minus infinity. If they approach 0 at the same rate, we might get a constant in between negative infinity and infinity. If this approaches infinity faster than this approaches infinity, we get infinity. If this approaches infinity faster than that approaches infinity, we get a constant over infinity that's going to approach 0. If they approach infinity at the same rate, then we might get a constant between negative infinity and infinity. So LHpitals Rule says if this is a 0 over 0 indeterminate form or an infinity over infinity indeterminate form, the limit, that limit that we're interested in, is equal to this limit. And I'll put a little h over the equal sign to denote that I'm invoking LHpitals Rule here. We're talking about relative rates of growth. We're saying if this one approaches infinity faster than this one approaches 0 faster than this one, and so on. Like, how can we measure that? We're talking about rates. Turns out you just use derivatives. So you take the derivative of the numerator, derivative of the denominator, and if this is a 0 over 0 indeterminate form or an infinity over infinity indeterminate form, LHpitals Rule says you don't have to evaluate that limit. You can evaluate this limit instead. Now that we know how to take derivatives, we can use this shortcut. We used all of these techniques before we knew how to take derivatives. Now this also holds if c is not a finite number. So if we have the limit as x goes to plus or minus infinity of f of x over g of x, and that is an infinity over infinity indeterminate form or a 0 over 0 indeterminate form. And it could be plus or minus infinity over infinity. We're not so concerned about the sign. If this is one of these 0 over 0 or plus or minus infinity over infinity indeterminate forms, LHpitals Rule says that limit is equal to this limit. There are lots of different spellings of LHpitals Rule. The spelling that the authors of the Larson and Edwards calculus textbook that we're using use is this this version. It's LHpitals Rule. And I'm sure I'm mispronouncing that. I'm saying it with my very American accent. Okay, but that's LHpitals Rule. And that's wonderful, because it allows us to get rid of infinity over infinity indeterminate forms, or 0 over 0 indeterminate forms, just using derivatives. Now these LHpitals Rule will apply to all three of these, but these techniques don't apply to this. But LHpitals Rule does apply to this. So let's use LHpitals Rule over here. First, we substitute in 0. The numerator is approaching 0 because we get e to the 0, which is 1. 1 minus 1 is 0, over sine of 0. Sine of 0 is 0. So this is a 0 over 0 indeterminate form. Well, according to LHpitals Rule, the limit of that function is the same as the limit of this function. Take the derivative of the numerator and take the derivative of the denominator and divide them. According to LHpitals Rule, these are the same thing. Well, the derivative of e to the 3x is e to the 3x times the derivative of the inside. The derivative of 3 times x is just 3. Derivative of negative 1 is 0. The derivative of sine of x is cosine of x. So then at this point you say, is this an indeterminate form? What happens to the numerator and denominator as x approaches 0 from the right this time? Well, I get 3 times e to the 0, so that numerator approaches 3, and the denominator is approaching cosine of 0, and cosine of 0 is 1. So this function's continuous at 0, you can just plug in 0. And that's the limit, so we just get 3 over 1, which is 3. Okay, so it looks like with this 0 over 0 indeterminate form, this exponential function and the sine function, we're approaching 0 at the same rate. Because we got a 3 over here. I think that's kind of cool. Okay. Let's look at another indeterminate form. Now I've got the limit as x approaches infinity of natural log of x over the square root of x. Now remember what this function looks like, these two functions. Y equals natural log of x looks like this. It grows. As x goes to infinity, natural log of x goes to infinity. It goes to infinity very slowly, but it slowly, slowly grows to infinity. So this is going to infinity. And of course, the square root of x is also growing to infinity. So this is an infinity over infinity indeterminate form. So we can use LHpitals Rule. So according to LHpitals Rule, this limit is the same as this limit. Now, after a while, when you use LHpitals Rule, you usually don't show this differentiation step. You just sort of do it. I'd be totally fine with you skipping this step if you want to. The derivative of natural log of x is 1 over x. And the derivative of x to the 1/2 is 1/2 x to the negative 1/2. Now, if I rewrite that 1 in the denominator, it looks like that. As x goes to infinity, the numerator approaches 0 and the denominator approaches 0. So this is a 0 over 0 indeterminate form. If you're thinking, oh, I have to do it again, wait a minute. We don't have to. you can actually simplify this algebraically first. So let's simplify algebraically and see if we can get rid of the 0 over 0 problem that way. I've got a fraction divided by a fraction. So I'll take the fraction in the numerator, take the fraction in the denominator, flip it, and multiply. And so we'll have a 2 in the numerator. And x to the 1/2 over x to the first. It's going to simplify that way. We'll have an x to the 1/2 in the denominator. If you do 1/2 minus 1, you get x to the negative 1/2, and then you put that x to the 1/2 in the denominator to write it with a positive exponent. Then you ask yourself, is this an indeterminate form? It's not. As x goes to infinity, I've got 2 over a very large number. 2 over a very large number is a very small number, so we get 0. What does that mean? Well, we're saying to ourselves, I've got infinity over infinity here. It's an indeterminate form. The result depends on which one goes to infinity faster. Now, I guess my question is, does this go to infinity faster, or does this go to infinity faster? Well, if the denominator goes to infinity faster, we end up with a constant over something very large, so we get something very small. So this square root function actually goes to infinity faster than natural log of x. It looks like natural log of x goes faster, but it's just because of the way I've drawn my graph. Natural log of x actually sort of flattens out much sooner than that. And this turns out to grow faster than that, despite my picture. Okay. So let's look at some other examples. Trying to make more space on my table here. Say we're letting x approach 0, and we're taking the limit of natural log of x plus 1 over cosine of x minus 1. As x approaches 0, we end up with a natural log of 1 in the numerator. And natural log of 1 is 0, so that's 0. And as x approaches 0, cosine of 0 approaches 1, so that's 1 minus 1, which is 0. So that's a 0 over 0 indeterminate form. You can evaluate that limit using LHpitals Rule. You take the derivative of the numerator and the derivative of the denominator and divide. The derivative of the numerator requires the chain rule because I've got that x plus 1 inside my log function. So you've got an inside function. The derivative of log of a function is 1 over that function. And then the derivative of the denominator, that's the derivative of cosine of x. It's negative sine of x, plus the derivative of negative 1, which is 0. Let's see what happens. Actually, let's take a limit from the right so that this limit exists. As x approaches 0, the numerator approaches 1, but the denominator approaches 0. Now, if we're approaching 0 from the right, let's look at the sine function. Sine looks like this. As we approach 0 from the right, sine of x approaches 0, but sine approaches from the positive side. The y values on the graph of the sine function as we approach 0 from the right are tiny positive numbers. So if I take that and I multiply by negative 1, this is a tiny negative number. So I have 1 over a tiny negative number that's going to be a large negative number. We'll get negative infinity. Okay, let's think about relative rates of growth with this. If this is a 0 over 0 indeterminate form, if this one gets to 0 first, we get 0 because we'll have 0 over a number 0. If this one approaches 0 before this one approaches 0, we have a number over something very small. Number over something very small is either positive or negative infinity, depending on the SIGN signs. So it looks like this one was approaching 0 faster than that one. And that's why we got negative infinity there. Okay, so we've looked at these two types of indeterminate forms and evaluated some limits that look like that. We're going to do these types of indeterminate forms next, and I think I'll probably do the last 4 indeterminate forms in another video. Now, LHpitals rule only applies in the case that you have a 0 over 0 indeterminate form, or an infinity over infinity, or plus or minus infinity over infinity indeterminate form. If you have one of these other indeterminate forms, you have to rewrite that expression so that it looks like this. Once it looks like this, then we're able to use LHpitals rule. If it doesn't look like that, we've got to do something else. We've got to do some algebraic manipulation in order to use this rule. Now let's talk about why a 0 times infinity would lead to an indeterminate form. A lot of students say, well, shouldn't you just get 0? Yes, sometimes you get 0. If this approaches 0 faster than that approaches infinity, so you've got a function times a function, and one function's approaching 0 and the other one's approaching infinity. If this one's approaching 0 faster than this one's approaching infinity, you get 0 times a number. Well, 0 times a number is 0. Now, if this is approaching infinity, that function that we're referring to here, if that function is approaching infinity faster than that one approaches 0, we end up with infinity times a finite number that's not 0. So we get infinity, provided that number is positive. So if this dominates, we get 0. If this term dominates, we get infinity, or maybe negative infinity, depending on the sign of this. And if this approaches 0 at the same rate that this approaches infinity, you might get a number like 17. You might get 4 or something like that. So the idea with all of these is that we've got to rewrite this. And if you have a product indeterminate form like this, a 0 times infinity indeterminate form, that can easily be rewritten as one of these indeterminate forms, as we'll see in the next couple of examples. Let's say we've got this. We have the limit as x goes to infinity of x to the 4th times e to the negative 2x cubed. Well, as x goes to infinity, x to the 4th, of course, goes to infinity. And this is e to the negative 2x cubed. So if x is a very large number, x cubed is even larger, and then if I multiply it by negative 2, that's a very large negative number. So this is e to a very large negative number. Now if we look at just a cartoon graph of y equals e to the x, we see that as x goes to negative infinity, so as what's inside that exponent becomes a very large negative number, the y values approach 0. So that's exactly what we have here. I have e to a very large negative power, large in magnitude, but with a negative sign. So this function is approaching 0. So this is an infinity times 0 indeterminate form. Now to get rid of it, basically what you need to do is take one of these factors and put it in the denominator. Multiplying by this is the same as dividing by 1 over that. I know that sounds a little complicated, but we'll talk about that in a minute. The idea is we're trying to write this as an infinity over infinity indeterminate form or a 0 over 0 indeterminate form. The way we can do that is by writing this an equivalent way so that the term ends up in the denominator rather than as a factor multiplying this guy. Now, if I have a negative exponent, the easiest way to do that is to rewrite that as 1 over the same function, but with a positive exponent. Then if I multiply straight across, we get this. X to the 4th over e to the 2x cubed. I don't have the infinity times 0 problem anymore. This function that was approaching 0, instead of writing it as a function approaching 0, I rewrote it as 1 over a function that was approaching infinity. It's 1 over something very large is something very small. And so now what do we have? As x goes to infinity, the numerator goes to infinity. As x goes to infinity, the denominator, that's e to a large power, so I've got a large number inside my exponential function, that's going to infinity. So this is an infinity over infinity indeterminate form. So now we'll just use LHpitals Rule. The whole point of the rewrite was we rewrote it so that we could use LHpitals Rule. The derivative of x to the 4th is 4x cubed. The derivative of e to the 2x cubed is e to the 2x cubed times the derivative of the inside by the chain rule. The derivative of the inside is my inside function, is 2 times 3, which is 6, times x to the 1 less power, so that's 6x squared. This is still an infinity over infinity indeterminate form, but we can simplify it. So let's factor out that x squared. That x squared will reduce with 2 of the x's up here, and you'll just have an x. So now we have the limit as x goes to infinity of 4x over 6 times e to the 2x cubed. And I guess we could have simplified these as well. Divide that by 2 and divide that by 2. So I've got infinity over infinity again. But that's nice. It's much nicer than it was when we had an x to the 4th there. It's just a 2x now. So when I take the derivative of the numerator this time using LHpitals Rule, I get a 2, which is very nice. Means we won't have to use LHpitals Rule a 3rd time. Well, I guess we used it once to get from here to here and then once to get from there to there. Yeah, we've used it twice. We won't have to use it a 3rd time. Derivative of the numerator is 2. The derivative of the denominator is 3 times the derivative of that exponential. The derivative of the exponential is the exponential times the derivative of the inside. The derivative of the inside is 6x squared. 2 goes into 6 3 times, and we end up with the limit as x goes to infinity of 1 over 9x squared times e to the 2x cubed. This is 1 over something very large. It's that something very small. And so the limit happens to be 0. So let's focus on what we just did. Basically, we took this function that was approaching 0, and we rewrote it as 1 over, it's like 1 over that function. I know that doesn't make sense, or it may not make sense, but it's sort of like, it's like this concept. Isn't multiplying by 1/2 the same as dividing by 2? So if I'm multiplying by something and it's approaching like 0, I can write it, instead of multiplying by that something, I can divide by 1 over that. So let's see, write that out. Instead of multiplying by f of x, we can divide by 1 over f of x, because dividing by a fraction is the same as multiplying by the reciprocal. That is going to allow us to get rid of this infinity times 0 indeterminate form every time. Because if I take this thing that's approaching 0, and instead of multiplying by 0, I divide by 1 over that function, well, that's going to get rid of that problem. I think I'm explaining it well over here, but I'm having trouble connecting it with this particular problem. Let me show you a different problem. So let's say you've got this type. This indeterminate form. You have the square root of x times sine of 3 over x squared. And you're taking the limit as x goes to infinity. Well, as x goes to infinity, of course, square root of x goes to infinity. That's a very large number. You take the square root, it's still very large. And then over here, as x goes to infinity, I've got 3 over x squared. So that's approaching 0. And now I've got sine of a function that's approaching 0. So sine of some number that's close to 0. Sine of a number that is close to 0 is a number that's close to 0 as well. So we have an infinity times 0 indeterminate form. Now there are 2 different ways that we can rewrite this so that LHpitals Rule applies. And we have to rewrite it so that LHpitals Rule applies. We can't conclude anything when we have an indeterminate form. All an indeterminate form tells us is that we have more work to do. So here are your options. You can either say, well, first let's write that as x to the 1/2. You can either say that multiplying by x to the 1/2 is the same as dividing by 1 over x to the 1/2, because dividing by a fraction is multiplying by the reciprocal. And if I multiply by the reciprocal of this, I get this. Or we could leave that x to the 1/2 in the numerator and say that multiplying by sine of 3 over x squared is the same as dividing by 1 over sine of 3 over x squared. So those are your 2 options. Now, one of those will turn this into an infinity over infinity indeterminate form, and the other one will turn it into a 0 over 0 indeterminate form. So let's look at it. As x approaches infinity, this approaches 0, so we have sine of 0, which is approaching 0. As x goes to infinity, I have 1 over a very large number. So 1 over a very large number is a very small number, so we have 0. So this is the 0 over 0 indeterminate form version of this. And I wrote a 1/2 or a 2 there. That should be a 1/2 power. Now the other option is to leave the x to the 1/2 in the numerator and then divide by 1 over this function. As x goes to infinity, this goes to infinity. And this is approaching 0. So we've got 1 over something that's approaching 0. So that's actually going to be plus or minus infinity, depending on whether this is approaching 0 from the right or from the left. Well, actually, we know that's going to be a tiny positive number. So this is sine of a tiny positive number. So that's a tiny positive number. So we get a positive number. So that's actually an infinity over infinity indeterminate form. So you have options. You can either rewrite it this way or this way. So let me write it out, sort of a guideline for you. To eliminate a 0 times infinity indeterminate form, this is what you should do. So if we're eliminating a 0 times infinity indeterminate form, given by the limit as x approaches c of some product f of x times g of x, you're going to rewrite that expression. You're either going to rewrite f times g as f divided by 1 over g, or g divided by 1 over f. One of those will be 0 over 0, the other one will be infinity over infinity. And that's the way you're thinking of it. You're saying as x approaches c, and c may be plus or minus infinity in this notation. So c might be finite, c may not be finite. If this is infinity times 0, if you put this 1 over g in the denominator, you're going to have an infinity over infinity. If you put the 1 over f in the denominator, if f was approaching infinity and g was approaching 0, this is 0, and then I've got 1 over something very large, so it's something very small. So if this is infinity times 0, this will become 0 over 0. If this is infinity times 0, this will become infinity over infinity. And the reason that works is, again, because dividing by a fraction is multiplying by the reciprocal. And that's so, this is because multiplying by f is the same as dividing by 1 over f. And it's just properties of fractions, no big deal. But that's how we handle that. Okay, so we've got two options here with this one. We can write it this way or this way. I think I would rather work with this. Let's try that. So I've got sine of 3 over x squared. I'll bring that x squared up to the numerator. I'll call that x to the negative 2. And then down here, I've got an x to the 1/2 in the denominator. So I'll make that an x to the negative 1/2. So this is a 0 over 0 indeterminate form now. And we can use LHpitals Rule. So according to LHpitals Rule, this limit is equal to this limit. I take the derivative of the numerator. Well, that requires a chain rule. I have sine of a function. The derivative of sine of a function is cosine of that function, times the derivative of the inside by the chain rule. So we'll have 3 times negative 2, that's negative 6, times x to the 1 less power. Negative 2 minus 1 is negative 3. Then in the denominator, we're doing the same thing. There's no chain rule, though, it's just a power rule. So we bring that power down, we multiply by x to the 1 less power. Negative 1/2 minus 1 is negative 3/2. And then we can simplify this. Negative 6 divided by a negative 1/2, you can multiply by the reciprocal, that's going to give us a 12 in the numerator. You can subtract these exponents. A negative 3 minus a negative 3/2, that's plus 3/2. It's going to be x to the 1.5 times cosine. It's all over 1. So that's going to be x to the negative 3/2, so I can put that in the denominator. It's an x to the positive 3/2 when I put it in the denominator. Okay, now let's think about what happens as x goes to infinity. As x goes to infinity, 3 over x squared still approaches 0. So I've got cosine of 0, which is approaching 1. So I've got 12 times 1 in the numerator, so I've got 12. 12 over a very large number to the 3/2 power, so it's a very large number. So 12 over something very large is something very small. That limit ends up being 0. Okay, so just keep this in mind. To get rid of an infinity times 0 indeterminate form, you divide by 1 over those factors, or 1 over one of those factors. So instead of multiplying by g, you can divide by 1 over g, or instead of multiplying by f, you can divide by 1 over f. One of those will be infinity over infinity, the other one will be 0 over 0. Let's do one last example of this. If the limit as x goes to negative infinity of x times natural log of 1 minus 1 over x. Well, as x goes to negative infinity, this is approaching 0. So I've got natural log of 1 minus 0. Natural log of 1 is 0. So that this factor is approaching 0, and x is approaching negative infinity. So that is a negative infinity times 0 indeterminate form. And you've got options. You can either take natural log of 1 minus 1 over x and divide by 1 over x, or you can take x and divide by 1 over natural log of 1 minus x, or 1 minus 1 over x. I think I would rather put that in the denominator and keep the log in the numerator. And if you're ever unsure of your algebra here, just simplify, multiply by the reciprocal, and see if it gives you the right thing. So we're keeping that log in the numerator, and instead of multiplying by x, I'm going to divide by 1 over x. And now, let's see what happens. The numerator still approaches 0. So I've got, this is approaching 0, natural log of 1 is 0. And then I've got 1 over a large negative number, so that's going to approach 0 as well. So this is a 0 over 0 indeterminate form, which means it's a good candidate for LHpitals rule. So according to LHpitals rule, that limit as x goes to negative infinity is equal to the limit of this function instead. Take the derivative of the numerator. So we get 1 over this inside function, because the derivative of log of a function is 1 over that function, times the derivative of the inside, and in the denominator we've got the derivative of 1 over x. You guys see that the derivative of this and the derivative of this are going to be almost the same. The only difference is that negative sign. Well, the derivative of 1 is 0, and then I'll factor out the negative. So I'll have negative 1 over 1 minus 1 over x times the derivative of 1 over x, all divided by the derivative of 1 over x. Now you don't have to do it that way. You could actually evaluate that derivative and that derivative, and then you'd see that they're the same except for the negative sign. And then you reduce them. And then you say to yourself, is this still an indeterminate form? What happens to this as x goes to negative infinity? This still approaches 0, and we have negative 1 over 1, which is negative 1. So that's our answer. Okay, so let's go back to our 3 types of indeterminate forms. If it's a 0 over 0, or plus or minus infinity over plus or minus infinity, according to LHpitals rule, the limit of this is equal to the limit of this. And if that constant is, if this c isn't a constant, but it's plus or minus infinity, it still works. That's LHpitals rule. Now, if you have a 0 times infinity indeterminate form, you have to do this technique that we talked about. You've got 2 functions multiplying each other, and we've got this type of indeterminate form. You pick one of them, and you divide by 1 over that function. So instead of multiplying by g, we divide by 1 over g, or instead of multiplying by f, we divide by 1 over f, And you can see that dividing by this fraction is the same as multiplying by the reciprocal. So that's the same as this. But once you've rewritten it in one of these two ways, you'll have a 0 over 0 indeterminate form or an infinity over infinity indeterminate form, and you'll be able to use LHpitals Rule. Okay, in the next video, we will look at these types of indeterminate forms, and then this type of indeterminate form, and we'll look at some other problems that look like indeterminate forms, but they're actually not. They're actually very determined, and we'll see what those look like, and we'll evaluate those,